Hello, I welcome you all for this supplementary video session for the course of Fundamentals of Automotive System in NPTEL program. In this session, we are going to discuss about how to test an engine, IC engine, for its performance characteristics such as power developed by the engine and various efficiencies involved and consumption like air and fuel. Before starting this test, let me introduce the test rig completely. This is the control panel for the test rig, and this is the engine we are interested to checking today, and this is the dynamometer. This is the engine we are going to test today. This is Kirloskar single cylinder 4-stroke diesel engine. This is a constant speed engine. The application of this engine would be in agricultural purposes. Let me introduce the components of this particular engine. This is the flywheel. As you see, the flywheel looks somewhat heavier as it is a single cylinder 4-stroke engine. It has to gain some momentum. That's why the flywheel becomes somewhat heavier. And this is the valve cover, and this is decompression lever. We will discuss in short. This is fuel injector where the high pressure diesel is injected into the combustion chamber, and this is a high pressure line. And in order to test the engine, we fit some sensor to measure the fuel injection pressure. It's a Piezotype sensor, and this is cylinder head. On the cylinder head, we have fitted one more sensor, one more piezo sensor, in order to measure the pressure involved in the combustion chamber. The purpose of the sensor can be discussed later. And this is the cylinder block. As it is a custom made engine, the compression ratio of this particular engine can be changed with these mechanisms. In a typical automobile engine, the compression ratio is fixed, so one cannot change the compression ratio. As it is a test rig engine, we do have a mechanism to change the compression ratio. And this is where you would put this handle. This is manual cranking engine where you would put a starting handle, and we need to start it by manual method. Now, as we discussed earlier, this is a decompression lever. What it does is, as it is a manual cranking engine, the compression pressure cannot be overcome by the manual effort. Since we have the decompression lever, it simply opens up the exhaust valve through mechanical linkages. Because of this, the compression process which happens in the combustion chamber is eliminated. As you see, as the lever is engaged, I could easily rotate this lever. Once I close this lever, the compression pressure is not allowing me to rotate the crankshaft. So, during starting the engine, the decompression lever has to be engaged. Then, through manual cranking, we have to gain some momentum. After gaining momentum, we have to gently close the decompression lever. Any engine cannot produce its maximum power without the load. In automobile or in a car or a truck, the self weight of the car or automobile is treated as load of the engine. In case of stationary engine, the engine needs to be loaded somehow. For that, we use a dynamometer. In this case, it is a eddy current dynamometer. There are many dynamometers used in engine testing. but we use eddy current dynamometer. In eddy current dynamometer, there are two important elements. One is rotor, the other one is stator. In this particular type, we have two stators that surrounds the rotor. The rotor is coupled with the engine flywheel. So whenever the engine runs, the rotor runs between the two stators. In stator, we have coil packs. This is the switch. As I turn this knob, the potential difference to the coil packs would be increased or decreased. As I supply the potential difference to the coil packs, it induces electromagnetic field, and during the engine motion, the rotor cuts it and it produces eddy current. The nature of the eddy current would be opposite to the direction of the engine. Thus, the engine feels the opposite load. The load of the flux, the strength of the flux is proportional to the turning in the knob. So as the stator try to stop the rotor, the entire stator itself try to rotate like this. So the movement is captured here in the S-type load cell. It's a simple strain gauge. So this is a S-type load cell. Due to reaction of the eddy current, the casing is tried to rotate on its axis. So please observe, as I push the casing, this is the load indicator. This has an error of 0.1 kgs. So as I push the casing, you would notice the load cell is capturing the load happening on the S-type load cell. So this is how the load over the engine is measured. And this is a rotary encoder. It serves two purposes. One is to capture the rotational speed of the engine, because the rotary encoder is coupled directly to the flywheel. So whenever the engine runs, it measures or it captures the rotational speed of the engine. Moreover, it gives a pulse for every single degree rotation of the crankshaft. What it does is, because of this pulse, with conjunction of the piezotype sensor here fitted in the combustion chamber, so for every single degree of the pulse, computer would records the pressure available on the combustion chamber. With this, one can easily plot the pressure versus volume diagram. We all know the area under the pressure versus volume diagram is going to be power developed by the engine. In this way, we calculate the indicated power of the engine. In the control panel, we have various displays. This one is a temperature indicator. We have 6 different temperature sensors fitted on the test rig, such as T1, that is temperature sensor 1, is helpful to indicate the temperature of the coolant which goes to engine, and this indicates T2, temperature of the water which comes out of the engine after cooling. T3 is the water temperature, goes to calorimeter. This is the calorimeter. I will come back to the calorimeter later. And T4 is the temperature of the water that comes out of the calorimeter. T5 is the exhaust gas temperature that goes to the calorimeter. T6 is the exhaust gas temperature that comes out of the calorimeter. Here T1 to T4 we use J-type thermocouple, T5 and T6 we use RTD. Here it displays the temperature values are displayed as the numerical value, that is, as we use a J-type thermocouple, it produces very low level potential, so it cannot be measured, so it has to be amplified. So what you see is not a temperature, we have a formula for this. So parameter equal to factor into V minus 1. What we see is voltage, that is V. So we need to substitute here. So factor is, for T1 to T4, the factor is 25. That means 2 minus 1 would be 1 into 25 would be your temperature, that is, in this case it is 25 degrees Celsius. So the J-type thermocouples are such a way calibrated, it shows the temperature in degrees Celsius. So in this case the T1 is 25 degrees Celsius. Suppose for example this is T2. So, for T2 voltage is 2.04 minus 1 would be 1.04 into 25, such that we need to see T3, T4. Now, this T5, the reading is 1.05. Here the factor for this T5 and T6 is 300. So, 1.05 minus 1 is 0.05 into 300 would be the exhaust gas temperature that goes to the calorimeter. This is how we measure all the 6 temperatures. With these 6 parameters, we can easily tabulate the energy balance sheet. This is the load indicator. As we discussed earlier, the signal is coming from the S-type load cell. It is a simple strain gauge. It has error of 0.1. So, whenever you apply the load on the engine, we have to subtract it, this 0.1 kgs of load. And this is speed indicator. So, as we start the engine, you could notice it is a speed. What is the speed of the engine? As this is a constant speed engine, this engine usually runs at the speed of 1550 to 1575 RPMs. And this is fuel measurement jar. This fuel measurement jar has got 2 modes. One is tank mode, the other one is measuring mode. Whenever the knob is in tank mode, the fuel consumed by the engine would directly go from the tank to the engine. If I flip the mode from tank to measuring, the fuel consumption would happen from the measuring jar alone, not from the tank. So, when the engine runs for the testing, we would simply flip the mode from tank to measuring. So, with the help of stopwatch, one would estimate what is the consumption of the diesel per minute. Similarly, we have a U-tube manometer. It has got 2 limbs. It is a water U-tube manometer. So, one limb is open to atmosphere, the other limb is connected to air box. What is air box? So, here this is the empty air box. So, from where the engine takes air, this is the intake line. So, whenever the engine sucks, the air has to pass through from this empty box. So, what we did is we connected one limb this to the empty box. So, whenever the engine sucks, the depression would be reflected in one limb. On the other limb, the atmospheric pressure is acting. So, the difference in pressure can be measured in terms of millimeter of water. It can be seen in a theoretical classes which is followed after this class. During running, one would see what is the difference in water level. So, that can be considered as the delta pressure across the U-tube manometer. And this is the load adjustment knob. As I turn it in clockwise, the load on the engine would be increased. If I turn it in anti-clockwise direction, the load on the engine would be decreased. So, this switch enables on or off of the load cell. So, we have 2 rotometer, one is for engine, one is for calorimeter. So, it measures, these 2 rotometer measures what is the flow rate of the water that goes to cooling of the engine and cooling of the calorimeter. So, this is the calorimeter. It is a simple heat exchanger where it has got 2 shells. On the inner shell, the exhaust gases would be passes. On the outer shell, we circulate the cooling water. So, what it does is, on the inner tube, as the exhaust gas passes, we supply the fresh water on the outer shell. So, the exhaust gases cools down. To what is the temperature to measure? We have 3 temperature sensor, among which 2 are RTD and 1 is J-type thermocouple, and this is T5 corresponds to the temperature that goes inside the calorimeter. This is T6 measures the temperature of the exhaust gas that goes out of the calorimeter, and this is a thermocouple corresponds to T4 measures the water temperature that goes out of the calorimeter. T3 obviously T1 and T3 are the same onto the engine and the calorimeter. So, T1 and T3 would be the same. So, the purpose of the calorimeter would be to evaluate the energy losses happen on the exhaust gases across the calorimeter. To cool the dynamometer, we have the cooling water, so cooling water in and the cooling water out. Now, we are going to run the engine and capture the parameters. During running, due to the noise, we may not discuss things in details. So, what I going to do is, I simply run the test and observe the parameters and note it down. In the theory class, we will be discussing how to calculate with those data points. So, before starting, we need to engage the decompression lever. Before starting the test, the engine has to run at the idle speed for at least 2 minutes in order to reach the equilibrium point. Then after applying the load, at that particular load, in this case it is 5 kg load, at this particular load the engine has to reach thermal equilibrium. Then only we need to conduct the test. Now we captured what is the fuel measurement for 1 minute, and subsequently it will be calculated as kg per hour. Then what is the difference in YouTube manometer in terms of millimeter of water, then what are the 6 different temperatures, and what is the load applied on the engine, what is the speed at which the engine was running during the testing. With these data points, we would be calculating brake power, and through the setup on the combustion chamber we fitted the Piezotype pressure sensor and the rotary encoder. One can evaluate the indicated power and friction power and efficiencies such as thermal efficiencies and mechanical efficiency, and what is the consumption happened for air and water. These calculation we will be discussing in the theory session. elaborately. Thank you.